For our next talk, we will have William Gustafson from the University of Kentucky, and he'll be talking about lattice minors and Eulerian posets. Go ahead.
Okay. Right. So the main goal of this talk here is to introduce for you a notion of deletion and contraction on lattices, which will, in a certain sense, generalize deletion contraction on graphs. And then from this, I'll define a poset of minors of lattices, and then I'll give a construction which shows that they're Eulerian, these posets of minors, and also that they have nice topology. So start with a few definitions. Okay, so a lattice is a poset in which for any two elements, we have a least upper bound called a join and a greatest lower bound which we call a meet. And yeah, so there's some equations what that means precisely. And then the other important notion here is that join irreducible. This is an element which covers exactly one thing in this poset. Okay, and this is like lining up with usual algebraic irreducibility. If you want to write it as a join, you need to use that element itself. All right, so here's a small example of a lattice, and the join irreducibles here are A, B, and C. And we'll come back to this example later. Okay, so now for the deletion and contraction, this is actually going to be defined on something with a little bit more structure than a lattice, but a lattice with a generating set. Okay, and when I say generating set, here I mean a set which contains the minimal element of the lattice, and then also generates everything of respective joins. Right? Okay. So with that, the contraction here is defined as, well, loosely, you take all the generators and you lift them up by everything in the set you're contracting by I. Right? So it's defined as this the lattice with this generating set. And then the deletion, more simply, you just take out those generators I. Okay, and then we'll refer to anything you get from a lattice L via these contractions and deletions as a minor. Okay, so let's see an example of that. So up here in the top left, I have the lattice or the face lattice of the square, and I just have like the elements here, the vertices in each face. Okay. So over here on the right is what you get when you delete by this first atom 1. And then we lose these two elements here because can't write them as a join with just 2, 3, and 4 as well. And then down on the bottom left is what we get when we contract by 1. So we get this upper interval, and we get these generators. Remember, we lift up by 1. So from 2, we get 1, 2. From 3, 1, 3. And then from 4, we join that with 1 to get 1, 2, 3, 4 as a generator. And on the right here, this is a little funny. If we take this lattice and delete the generator 1, 2, 3, 4, we get the same lattice since 1, 2, 3, 4 is still the join of 1, 2, and 1, 3. But these are being considered as different minors, okay? Because the minor is really a lattice together with a generating set, and these are different generating sets. Okay, so that's the notion of deletion and contraction. And I said this was going to generalize deletion contraction on graphs in some sense. So let me talk about that now. All right, so if you take a graph and give it a vertex labeling, and then look at its lattice of flats, then the simple vertex labeled minors of G, when I say minors, I mean delete and contract edges, not vertices. Those are in bijection with the minors of the lattice of flats. And a bijection is what you want it to be. Just take the lattice of flats of the graph minor. Okay, so let me show you a picture, and I'll give you like a little bit of idea of how that works. So up here I have a graph of a vertex labeling, and then here's its lattice of flats as partitions. So these are all the partitions that you can get from this graph as the connected components of a subgraph. So for instance, this partition 1, 2, 3/4, you can get as the subgraph. It's connected components as a subgraph where you take the edge 1, 2, and 1, 3. Okay, and then down here, this is the simplification of the graph we get by contracting the edge 1, 2. So when we do that, the edge 1, 3 and edge 3, 2, right, you get like a double edge like this, and I've identified them. It's a simplification. And there's this lattice of flats. You can see if you were to contract in this lattice by this atom, 1, 2/3/4, you get this lattice flats. Okay, then here's the deletion by 3, 4 in the lattice of flats. And again, in this graph, that's the deletion by this atom. Okay, and the idea of the inverse bijection, going from a lattice minor back to a graph here, is that the minimal element in your lattice minor is encoding the vertex labeling. Right? This is telling you 1 and 2 is a single vertex. And then the atoms here tell you what the edges are. You get all these from the minimal element by merging 2 blocks. So that says, hey, those 2 vertices are connected. Okay. So now the main object that I want to tell you about is the poset of minors of the lattice. Right, so here's our definition of that. It's simply the set of all minors of a lattice with a specified generating set. And then we partially order them. Essentially, you go down by deleting or contracting. And then I'm also going to add a minimal element, which I'm going to denote empty set, so we don't get confused with the 0 hat in the lattice. Okay, and I'm denoting that by ML here. Okay, so let's look at an example of one of those. Okay, so up top is that lattice of 5 elements that we saw earlier. Okay, and this is its associated poset of minors. So if we look at the coatoms, for instance, this is deletion by C, deletion by B, deletion by A. This is contraction by A. And then where are the contractions by B and C? Those are down here. Those are lower rank because there's like some collisions. So here when you contract by B, A will go to B. So you could have deleted it or contracted it beforehand. Those are up here and here. So that makes it lower rank. And here when we contract by C, A and B both go to the the 1 hat maximal element. So you could have deleted A or B beforehand, and that makes this lower rank. Okay, so 2 interesting things you might notice is that, so this poset here is graded by the number of generators. There's 4 generators, 3, 2, and 1 generators. And then another interesting thing is that these atoms all correspond to the 5 elements of this lattice. Okay, so now I want to just go over a couple basic results to hopefully give a little bit of intuition about these posets, and then we'll move into the construction. Okay, so this first proposition, just these first 2 things are what I just said, that atoms are always going to correspond to the elements of the lattice, and they're always graded by the number of generators. And then here, the rank 2 elements are not so bad to describe either. So you pick an element for your minimal element of that minor, and then you pick a join irreducible to go up by. Okay, and they also happen to be thin. But okay, the second proposition here, this gives us another way to think about minors. So let me go on a little aside first. If you think about that notion of deletion contraction, there's only joins in it, right? No meets. So if you prefer, you could think that this is not really thinking about lattices, but to think about what's called a join semi-lattice when you maybe don't have a meet operation. I'm really only looking at finite lattices and all these join semi-lattices have a minimal element because that was something we prescribed in our definition. So they're lattices anyways, but the point here is that since we're looking at join semi-lattices with a minimal element in some sense, the Boolean algebra is the free object there. It's not the free lattice, but it's a free bounded join semi-lattice. And from that, we get another way to think about minors as like they're inherited from the intervals of the Boolean algebra. So that's what's this saying here. Right? If we look at this map, this is like the canonical map from the Boolean algebra to a lattice. You just take a set to corresponding join of irreducibles. Then the image of the intervals give you the minors exactly. So, but to tell you, what minor you get, I have to tell you the generating set. The generating set is like inherited from the intervals. It's the generators are the image of the atoms in the interval. Okay, and then if you look at the Boolean algebra, the minors are exactly the intervals. And so the minor poset of the Boolean algebra will give you the interval poset, which is the face lattice of the cube. Right, so that will come into play with this construction here, which I'll go into now. All right. So the setup for this construction is we have 2 lattices, L and K, with specified generating sets. And we have a join preserving surjection from L onto K. And then this descends to a surjection from the generating, sorry, excuse me, got gas. But this descends to a surjection from the generators of L onto the generators of K. And with that set up, the poset minors of K can be obtained from the poset minors of L by a sequence of something called zip operations. Because this is the zip operation introduced by Nathan Redding. All right, and the theorem of Nathan Redding's is that the zip operation preserves Eulerianness. Oh, sorry. First, I want to say the zip operation, I'm not going to go into it, but you should think about it as a like certain nice cell contractions on a cell complex. Okay, we'll see that in just a moment. But the zip operation preserves Eulerianness and PL sphericity. And since the cube is Eulerian in a PL sphere, and we have such a map from the Boolean algebra to any lattice, we can do these zip operations from the cube to get any minor poset. And that shows that they're Eulerian as well as a PL sphere. And then another corollary that I get from this, there's a formula that Nathan Redding gave for how the zip operation affects the CD index. And using some positive non-negativity results, you get these inequalities here for the CD index. So I don't have time to go into, but this is a certain non-commutative polynomial, which like very compactly encodes chains in your poset. Okay, so now to end with, I just want to give you an idea of how this construction looks. Okay, so up at the top here, I've got the Boolean algebra on 3 elements and this lattice from before. And then we're going to map from here onto here by sending 1 to A, 2 to B, 3 to C, and then it's join preserving. And then the idea is to view this map as a congruence. So when I do this map, 2 and 1, 2 are going to go to the same place since A join B is B over here. And then all these 3 elements here, oops, it clicked, sorry. Yeah, so the 3 elements, 1, 3, 1, 2, 3, and 2, 3 all go to the 1 hat. So these blue lines are indicating the non-trivial equivalence classes in the congruence. And then the idea is to build up this congruence, sort of identifying 2 things which are connected by an edge at a time. And to make sure we keep a lattice in between, we have to start with the top edges. And as we do that, we'll do these zips, these cell contractions on the associated complex. So here I have the cube. Remember, that's a minor poset of the Boolean algebra, or its face poset is that. And we start by identifying these 2 elements. And so I contract this edge here to get this complex. And the face poset of this complex is the minor poset of this lattice. And in the next step, I'll identify these 2 elements to get this lattice. And on the complex, I contract this edge to get here. Now I have a square kind of coming around and a two-gon on the side. And I need to zip the two-gon. And so the reason for that is because it's coming from this minor with 3 elements. And these 2 things are generators, but they're being identified. So I need to identify it with its 2 edges. So we zip the two-gon, contracting it into an edge to get this complex here. So it's getting hard to read, but there's a square coming around, triangle on top, triangle on back, another square and square on bottom. And the face poset of this complex is the minor poset of this lattice. And then in the last step, I identify these 2 elements. So I zip this edge to get here. And I get another two-gon coming from minor these 3 elements. Again, these are generators. And so I have to zip that to get this complex where there's like 2 squares, 2 triangles. And face poset of this complex is the minor poset for this lattice here. Okay, so that's all I have for you guys today.
All right, thanks, Williams. And let's thank our speaker for his presentation. So is there any question from the audience?
So can you use this notion of lattice minors to give some kind of forbidden minor characterization of any interesting lattice properties, as is often done with graphs?
Yeah, so thought a little bit about that. One class you can do is geometric lattices. It's very easy, so maybe not very interesting, but it's like a 2-chain. So it's pretty straightforward to prove that, yeah, that no 2-chain as a minor is equivalent to atomic and upper semi-modular. There could be hope for distributive lattices. These are closed undertaking miners as well, but it seems to be more challenging.
Thank you.
Any other question for our speaker? So it seems like you both mentioned some results from Nathan Redding's work, and is there like a particular or two references that you recommend people to look at, for example, for like the notion of zip operations that you use in the talk?
Yeah, this zip operation was introduced in Nathan Redding's paper, the CD index of Bruhat intervals. So in that paper, he introduced the zip operation and used it to study intervals in Bruhat order of Coxeter systems. Used it to get like a structural recursion and used that to show their PL spheres.
Right, thank you.
Yeah, and the theory of shards, which I just briefly mentioned at the end of mine, comes up in Redding's lattice quotients, or sorry, lattice congruences of the weak order. Although the representation theory connections are in a different paper by, I think, or in a different paper, which I would need to call up briefly, I'm afraid.
That's all right. All right,
But,
thanks. Thanks, Paul. So, is there any other questions from the audience? Or if there's no more questions, let's thank our speaker again.